Hey there, physics students. So in this video, I'm going to go over what those lab reports should look like. And this video is the second video I've done because the last one I didn't record any audio with mine. Apparently, the default setting was no microphone at all, so that's sad. But anyways, first thing I did is I went through because there are different, there's a couple different options for the lab. So what we're saying here is design a lab procedure the students could use to determine blah, blah, blah. Okay. For this particular thing, it's mass of the unknown object, or excuse me, it really should say unknown mass of the object, but there you go. And then I filled that in all these other places where that blank is mass of the unknown object. And finally here, mass of the unknown object. So I'm going to walk you through this. The first thing here, this doesn't exist on the current version of the exam, but it's not a bad habit to be in, is to tell what I'm going to measure and what I'm going to measure it with, because that is one of the things that you get points for, is telling something like, I'm going to measure the mass of the cart with the balance, and I'm going to measure the acceleration of the cart with the motion detector. So you'll just have a place to enter to write that procedure down. So what I said here, and by the way, this is the thing that I gave you. So there are some constraints on this system. So I said, okay, you can have a cart and a string and tie it to an object of unknown mass, and you can add masses to the top of the cart. You can measure the mass of your stuff with the balance, and you can measure the acceleration with the motion detector. So there you go. So measure the mass of the cart and the objects on top of the cart with a balance. I called all of that together mcart. You could have called it something else if you wanted to, but that's just how I chose to do it, because I wanted to differentiate mcart from mhanging, because that's going to be the object we're trying to find the mass of later. All right, so anyways, we're gonna go through this thing, like, you let it go, the system's going to accelerate. So we release the system, we measure the acceleration with the motion detector. Be intentional about this. Make sure you're saying measure mass with the balance or whatever. Measure this with that. Make sure you tell those things, because that's one of the things you're getting points for. Now, the way we're going to get multiple trials out of this, we can't change the unknown mass, but we can change the mass of the cart. So that's what we're going to say here, is just vary the cart mass as you do several different trials. That'll take care of the repeating the experiment part. And like, okay, what's going on here? How do we figure out what to graph down here? So we're going to go back to Newton's second law and look at this relationship. And we're like, okay, so the acceleration is the force sum divided by the mass of the system. And what we can do here is we can be like, okay, what's the force sum acting on the system? Well, we chose to ignore friction of the rolling cart. So what we're going to look at here is like, okay, the hanging mass is the thing that's pulling the system along. Now, the mass is not a force, but gravity is a force. So that's why I said, in place of the force sum, I said hanging mass times g. That's the force of gravity. Then we're going to divide that by the total mass of the system, and that's going to equal the acceleration. Well, what can we measure? We can measure the motion. We can measure the acceleration with the motion detector. So we've got the acceleration. We want to know the hanging mass. G is a constant, so we know the value of that. And then the total mass is really close to the mass of the cart, because I told you in the lab to pick a light object, something that wasn't very heavy. So we're going to make this assumption that the total mass is just the mass of the cart. Now, I don't think this particular question would appear on the AP exam, because I don't think they would expect you to make that assumption. The math here gets kind of messy. You can still do it, but it gets kind of messy if you try to do mass of cart plus hanging mass, and then you're trying to graph stuff like that. Doesn't work out very well, but this is nice and clean if you do it this way. So what I did is I just replaced m total with m cart, and then I factored the m hanging out and just left the g over m cart. So it's just like this. I would have had m hanging times g over m cart, and then I just factored the hanging out, so it looks like this. Now, why did I do that? Because I want to figure out what to graph on the different axes, well, I can measure the mass of the cart. I can measure the acceleration. So if I put acceleration on the y-axis and I put g over mass of cart on the x-axis, then the hanging mass is going to be equal to the slope. And that's really what you want to do, is you want to get this thing where you're going to get something that's just like, it's either going to be the slope or the intercept. Usually the slope based on historic, something about the graph. You're like, okay, what are the characteristics of the graph? Well, there's either the slope or the intercept of the graph. Like that, there's not a lot else that you can do with a graph. So in this case, we're like, okay, if we graph acceleration on the vertical axis and we graph g over mass of the cart, and that's what I said down here too, or up here, then the slope will equal the unknown mass. Now, you could go in depth more than this. You could say, plot the acceleration and g over mass of cart points for, and by the way, that's just going to be 9.8 divided by your cart masses, or you could even do 10 for g instead of 9. But anyways, you're plot all the points, draw a line of best fit, find the slope of the line of best fit, then the slope of the graph line, or the slope of the line of best fit, will equal the unknown mass. I think for the purposes of the reading, if you're just telling us that the slope of the graph line is equal to the unknown mass, that's probably going to be good enough. Now, so we go through, we do our points, we measure the acceleration, we did the g divided by mass. So I think their first run, thanks to Danielle and company for this data, their first run, I think they did like just the cart, so it's half a kilogram. So they did 9.8 divided by 0.5, and that gave them 19.6, and then whatever the next one was, and so on and so forth with those values. Then we have to graph the values. So they want you to use at least half of the space on the graph, and the way I look at that is you're going to use at least half of each axis. So we need to scale our axes so that that's going to work out. Our biggest value on the vertical axis was 0.17, so I looked at this and just kind of thought about it for a minute. Okay, if I do 0.05s, 0.05, 0.10, 0.15, 0.20, 0.17 is going to go above half of the graph. Half would be at 0.15, so that's going to work. And then my biggest one for G over M was 19.6. So I looked at it and said, well, if I make this two lines, or two big lines, equal to 5, like that would be 2.5, 5, 7.5, 10, 15. So like that's going to use the entire horizontal axis. So you're like, yeah, that's good. And don't worry about this thing. Like, we got some dead space over here. That's because we had to have that space. So this would be fine. On the AP exam. Now, you got to plot the points within reason. Don't do anything crazy here. They're not going to be like, if you're off a little bit, it's not a big deal. It's if you're like pointing totally and they can tell you're totally plotting the wrong points. Then once you plot the points, they're not going to be a perfectly straight line in all likelihood. So you're going to take some kind of straight edge, and you want it to fit the data. You're not connecting the dots. You just want it to go through the data and be a reasonable representation of the data. So you're going to line that thing up and draw a line on it. I did that in the last video, but Now, other things you got to do to get points. So plotting the points is a point. Drawing the line is a point. By the way, the points and the labeling of the axes go together, or at least the numbering of the axes go together, because if you don't number the axes, we don't know what you plotted, so there's no way for us to give you that point. And you got to label the axes. So acceleration is the variable graphed, and then we got to give a unit for that quantity. So meters per second squared there. And then G over M, I know the unit for G is meters per second squared. I know the unit for mass is kilograms. Don't worry about simplifying those units. Like literally just put the unit for, if you're doing, something divided by something or something squared, just square divide the units or square whatever thing you're doing. So don't get caught on trying to simplify those units, because it'll still get counted correct even if you don't simplify the units. As long as units that you put there are correct for whatever quantity. Now, what I said down here, I used Desmos to get the regression. It gave me y equals 0.0136 x minus 0.099. The thing I said was important was the slope, and I'm going to very explicitly say the slope equals the mass equals 0.0136 kilograms, and that would be the same as 13.6 grams. You don't have to say that, just get the kilograms. That seems like a reasonable one. I think they were using like an eraser or something, and maybe it wasn't exactly 13.6 grams, but that's close enough for us to be like, yeah, there's some kind of validity here. The other thing I thought about was maybe that negative intercept does actually mean something too. I bet that is the acceleration calls, because look, the acceleration axis, so the value here, the negative 0.099, would be a negative acceleration. I bet that's the acceleration caused by the friction in the wheels of the cart, or maybe the cart wasn't quite level, or the track might not have been level. So somehow or another, and I just got curious. I went through and said, this has nothing to do with answering the question, by the way. But I was just curious, how many newtons would that be if it was just acting on the cart? So that's a really small number of newtons. So that might be friction. It might be the table wasn't quite level, and that was causing some resistance to the cart going, or hindrance to the cart going forward. So somehow or another, there's something going on there. But we still got a nice linear data set. In fact, I was very surprised with the lab results. The data sets were great for just about everybody. So that was pretty cool. So I hope that helps. And yeah, you should get lots of points on lab questions, because it's not so much about, you have to know some physics, but a lot of it is just graphing skills and math stuff that you can, and writing a procedure that tells to measure something with the equipment you're given and repeat the experiment. So there you go. You should get at least half the points on the lab question every single time. And thanks for watching.